Now, how we regulate this pathway? I think you might feel almost obvious that okay? No fire alarm or anything. I'm for it. It's just raining. So I want to tell you that it's really unlikely that in a same cell, the two pathways, let's say glycolysis and gluconeogenesis, act together. So there must be a way to regulate one versus the other. So that concept is relatively complex, and there is a lot of factors in, starting with hormone regulation to the specific regulation in some of those enzymes, in particular those far away from equilibrium. So that means that metabolic pathway in the cell is not looking like this, classical traffic needle, but must more look like something like this. Very organized with many signs saying stop, hold now, free way, and things like that. Reduce your speed because red is coming, is orange right now, and things like that. So, the types of regulation that we saw can be divided in two major categories. One is that one that acts slowly or very slow, and another one that is fast, cellular concentration of reagents fast, so very sensitive to what is happening to the cell. So for those guys, could be the enzyme localization. You know, if an enzyme works in the cytosol and there is a regulation that makes, or a signal that makes that enzyme move in this nucleus, that is a way to control the activity of the enzyme because the concentration is reduced. Even slower is when the enzyme can be degraded and has to be re-synthesized. In that case, it's really the most slow one, who takes weeks. Okay? So on this other side, we have the fast situation. So the fast situation are really the quick readout that is happening in the cell in that moment. So we have substrate level control. So if the substrate is a lot above the peak level of that enzyme, if we increase more that substrate, the enzyme will not speed up much more because it's already above its peak level. The change will be small. We will see that better today. Instead, if the concentration of the substrate is normally below the peak level of the enzyme from that substrate, any increase will be a lot of increase in terms of the velocity of the enzyme. Feedback control and product inhibition, those two are related to elements of the pathway that can go back to the first enzymes. Then we can have how those happen. Could be by allosteric effectors or by covalent modifications. Allosteric effectors, imagine what hemoglobin did to oxygen did to hemoglobin, right? They increase a lot of the affinity of the enzyme of the molecule for other oxygen molecules. So if we have a multi-subunit enzyme with more than one binding site for the substrate, that has to be a requirement, right? If something binds by the way the enzyme is affinity for the substrate for all the other subunits can increase and the enzyme can act faster. Covalent modifications like phosphorylation, dephosphorylation, we will see examples. So the substrate level control is a consequence of a low mass action. You remember lecture 4, I believe, between 3 and 5. And it's is relevant for all those enzymes that work at equilibrium eventually. Because they get very little substrate, and for sure their ketoneme is, for that substrate, is higher than the concentration of substrate. So that is the general rule. So this is more actually for those enzymes that are in equilibrium. However, the example that I'm going to provide you today is not one of those enzymes. It's hexokinase, which is actually the first enzyme of glycolysis. In that case, it's even more important. So we can consider it like a sort of special case. It's a special case because hexokinase has at least 4 isozymes, so 4 variants of the same enzyme. And the hexokinase 4 is the only one behaving this way. This hexokinase 4 is only in our liver, or in general liver. And there is a specific reason. It's because the liver is the big factory that is in our body to produce energy, mobilize glycogen for the blood and the other part of the body, for the brain, for example, and making glucose this way, or to transform from energy, transform that energy into fats. So, I think I showed you this also before, is that the Q and equilibrium constant. You remember the ratio between Q and equilibrium constant has to be below 1 in order to have homeostasis. We had that around, and our final conclusion about that was this delta G is equal RT natural logarithm over Q divided K. Only with the ratio between Q and K below 1, we can have a negative delta G, and that is how it's working. It's also not only spontaneous, but also in the so-called steady state. We also find out what could be the characteristics of a reactions or a pathway or organism to have this, to fulfill that ratio below 1. And there were different examples. For instance, there was the concentration of products must be low. So the next enzyme, ketoneme, will be higher than the substrate concentration, and that will help also to regulate that enzyme. Also, the concentration of reactant in some situation, like in the first enzyme, has to be high. So that is because the first enzyme usually are slow. The results of that is that the reactions are going only in one direction, and these possible equilibrium arrows are impossible to reach. They can be reached, equilibrium can always be reached by those enzymes, but only if you take that enzyme and put in a petri dish, in a reaction tube along with this substrate. With time, we will reach equilibrium like any reaction will do. But in this case, very likely it would never happen. So let's try to visualize substrate level control with a chart, because I think it's probably the easiest way. Here we have the concentration of the substrate, which could be expressed in terms of times for ketoneme. You remember ketoneme identified alpha B max, and imagine that we have a situation like this. Physiological concentration of the substrate at this level, 3 times ketoneme, even more. So the slope that identify the rate is kind of flat, and even if you increase a lot, increase the substrate, there will be no much increase in velocity of the enzyme. On the other hand, if you take a situation like this, the substrate concentration is about half of a ketoneme. The slope here is higher, and the rate of the enzyme has still space to go higher, just with a little increase of a substrate concentration. So let's see. From here we go there, or from here we go there. Here, oops, sorry, there is not much increase. Here, there is a lot of increase in rate. That is how substrate control concentration for a reaction works. So, as I said, all those reaction equilibrium in a theoretical pathway, they all get advantage of that. So if there is some big changes in the activity of the rate control limiting reactions, which are the store enzymes, that can be reflected also in all the others, because they receive the substrates in a lower concentration that they keep on for that substrate. So they have a room to increase the rate of reaction. An example, the example that I'm giving you is not exactly one of those enzymes, because that is already kind of what I showed you before. It is another way to control glycolysis in the liver. And I will review that also when we will do more about the glycolysis. So we have exokinase. Exokinase transforms glucose in glucose 6-phosphate. Here. So this reaction is requires energy, so there is ATP involved, and is slow. So this is one of the reactions that makes the glycolysis under control. However, it's not the main one, at least in the muscles. In the liver, indeed, maybe this is the most relevant one, because instead you have exokinase 1, 2, and 3, which are very common in our muscles, in the brain, and so on. The liver has almost only exokinase 4, which is a variant of exokinase, it's the same enzyme with little difference, which has a very different K-con-M for the substrate. So while these guys, 1, 2, and 3, have a K-con-M of 0.2 millimolar, exokinase 4 has 10 millimolar. Something that you want to learn and don't forget. The concentration in the blood of glucose in an healthy person should be always around 5 millimolar. And that is how should be transferred also into the cell. If it's going too high, there's issues, and stay too high. If it stays too low, it's very dangerous as well. So, when we have a million, and this can go also higher, while these guys don't change at all this ability to digest or start the glycolysis, transforming glucose in glucose 6-phosphate, this guy has a lot of room because it's very far away from its K-con-M. So this is how, I think, a specific example of substrate control in glycolysis, and actually the first example of glycolysis in one specific organ, the liver. Now is a little bit too early. In a couple of lectures, we'll be able to really have a better picture of what we are looking at. The muscles and the brain will be very similar. The only difference is that the muscles have their own storage of glycogen, so glucose. The brain doesn't have. So the brain relies always on the glucose that the liver is mobilized by degrading the liver glycogen and putting those glucose in the bloodstream. So in other ways, when we have a glycolysis from a glycogen, that we will learn also a little bit later, in the muscles, we don't even need exokinase, because we get just a minimal part of a glucose. The molecule that we get will be glucose 1-phosphate, and then that will be transformed into glucose 6-phosphate. So we don't even need exokinase in the pathway that involves glycogen in the muscles. In the liver, the situation is slightly different. Okay, so product inhibition. that was the other example. Product inhibition really looks like competitive inhibition. The only thing now is that the competitor is not a poison or a molecule that is coming from outside by an insect or an animal that use that as a venom. It's just the product of our reaction. And that is a way to tell, we are going too fast, calm down. Also because if that product accumulates, means that, you remember the pathway, means that the next reaction is not picking up it. So this is why it's accumulating, and this is why it should work to reduce the reaction rate. So we already have done that. We know that Vmax doesn't change. Kconm becomes Kconm apparent, which becomes bigger. So in that way, the enzyme binds less reactant, so we make less product. For product inhibition example, we use again exokinase, all the 4 exokinase can work this way. So another way exokinase can be controlled is because the glucose 6-phosphate can still bind exokinase and block the binding of glucose. Okay, so this is the second way exokinase can be regulated. Exokinase has a lot of regulation. So, little example. I forgot even what I wrote there, so I have to read again. So we have I'll imagine you have still a kind of exokinase, but only focusing on competitive inhibition, not the other type of inhibition. And assume, glucose 6-phosphate is and glucose are respectively inhibitor or product, but also the substrate for glucose. So what will be the effect of the inhibitor, glucose 6-phosphate, assuming that Kconm for glucose is 1/5 of Kconm for glucose 6-phosphate. So if we have a 1.2 millimolar of glucose 6-phosphate and 0.4 millimolar of glucose, or if we have a 4 millimolar glucose 6-phosphate and 0.0 millimolar of glucose. How we should think in this way, on this question? We should figure out or decipher what this means, right? There is no number there. I didn't say 5 and 500 or 500 and 5. It's X and 1/5 of X. So if Kconm is 1/5 of glucose, is 1/5 of Kconm of glucose 6-phosphate, means that the Kconm for glucose is 5 times smaller than the Kconm for glucose 6-phosphate, right? So has a much more higher affinity. The enzyme has higher affinity for glucose respect to glucose 6-phosphate. How much? Around 5 times this point if we keep the proportion. So if we have 1.2 versus 0.4 and 4 versus 0.4, now becomes relatively simple. This one is 3 times more than that, while this one is 10 times more than that. Okay? So if a glucose 6-phosphate is 10 times more concentrated than glucose, and this Kconm is 5 times more than that one of glucose. Now we can imagine roughly that there is 2 more chances to bind the glucose 6-phosphate instead than glucose because it's so much more abundant in the latter case. While this one, yes, might still affect a little bit, but will be a small percentage. This is very qualitative. We are not making, real numbers calculation. Okay, it's just algebra that we are using. And just to make you safe, I don't think I would have questions like this in the exam, but grasping these concepts might help you to answer other questions. Okay. So, and here I had an application, you can go through that by the. So, feedback control is another way to, very similar to substrate control, but instead to be just the product of that reaction, might be the end product of a pathway that if accumulates can go back and reduce the affinity of the enzyme, the first enzyme, for its own substrate. So in this case, it's E that is going back. In this case, it's a little bit more complicated. It's a pathway that is branching in 2 ways. And if this way is going too high, F is able to reduce the production of itself, but enhance the production of the other parallel pathway. Eventually, G and N are needed for something that they make in the cell in the same amount. Imagine purine and pyrimidines, for instance, right? So, allosteric enzymes, they behave inhibitors. This is a non-cooperative enzyme like we have seen so far. An allosteric enzyme will work in this way, very much like hemoglobin. So we cannot go and replicate all the story that we did for hemoglobin for an enzyme, but very much the things resemble each other. And here we see, especially for an enzyme that has symmetric allosteric, like hemoglobin has symmetric allosteric, we have a R and T conformation, and you see huge difference in rate of reaction. This is the R, this is the T, and this is non-accretive repressive, so a midway in which the enzyme was in this one. So not much difference, exactly like we saw for hemoglobin myoglobin. And we could still have also sequential cooperativity as well. Let's say the enzyme, which has to be multi-subunits, with more than one binding site and catalytic site of the substrate, has its own subunits not tightly linked, but weakly linked. So when the substrate binds one, maybe that will reflect only to another subunits, the increase of cooperativity or affinity, but not in all the others. I think now we take the attendance.